Hi all, this is Vishwanath Verma Indukuri and I'm here to do my presentation 5. So the first article is Mastering the Game of Go with Deep Neural Networks and Research. So going into it, the abstract. So the game of Go has traditionally been recognized as the most difficult of mainstream games for artificial intelligence due to its large search area and the difficulty of judging board situation and moments. So here the authors present a novel computer Go strategy that analyzes board positions using value networks and determines the moves using policy networks. So using this research methodology, the curriculum of AlphaGo vanquished the human European Go champion by a score of 5 games to 0 and had a victory of 99.8%. So it was the first time a computer algorithm has conquered a human professional player in a complete game of Go, a feat that was expected to take at least a decade. So to train these deep neural networks, an inventive pairing of supervised learning from human expert game and reinforcement learning from self uh, play sport has been used. So the role of neural network Go to level of cutting edge Monte Carlo research systems, which simulates thousands of random self-play games using any look ahead search algorithm. So a new search algorithm also presented, which combines Monte Carlo simulation with value and policy networks. So next comes the introduction. So these games can be solved by iteratively computing the optimal value function in a search tree with which is about potential move sequences where B is the game's breadth and D is the game's depth. So exhaustive search is impossible in huge games like chess and notably Go game. By the effective search space can be lowered by two broad principles. So using multiple layers of neurons arranged in overlapping tiles, they created more abstract, localized representatives of an image. So we can use a similar architecture for the Go game as well. So convolutional layers are used to generate a representation of a board position, which then passed is a data set of 1919 images. So we can use these neural networks to reduce the effective depth and breadth of the search tree, and a value network evaluate places, and a policy network samples the actions. So the supervised learning of policy networks. Uh, so supervised learning is also known as comes under the machine learning, which is a subcategory of the artificial intelligence. So it can be defined by the use of labeled data sets to train algorithms that accurately classify data and predict the outcomes. So in this supervised learning policy network, convolutional layers with weights and rectifier nonlinearities alternate. So for all permitted moves, a softmax layer generates a probability distribution. So for the first step of the training pipeline, we improve on the authors improve on previous work by using supervised learning to predict expert movements in the game of Go. So neural network training pipeline and the architecture. So in a data set of positions, a supervised learning policy P and a quick built out policy P are utilized to predict human expert moves. So in comparison to previous policy network versions, reinforcement learning policy network P is added to the supervised learning policy network, and afterwards it is augmented by the gradient descent learning to maximize the outcome. So playing self-play games with the a reinforcement learning policy network generates a fresh dataset. So using the stochastic gradient ascent to maximize the likelihood of the human move, selected in a sample state action glance, S comma A, where A is the value network and V is trained by regression to predict the predicted outcome. So next is the reinforcement learning of policy network. So to improve the policy network, the second phase of training pipeline employs a gradient descent reinforcement learning. So the uh, reinforcement learning policy network P has the same structure as the supervised learning policy network. So the plot depicting the playing strength of policy network as a function of the training rightness. So the victorious rate of AlphaGo using the policy network versus the AlphaGo's match version were plotted. So during this training, the policy networks with a combination of 128, 192, 256, and 384 integration of different per layers were frequently examined. So reinforcement learning of the policy network. So next comes the value network employs multiple convolution layers with parameters, but instead of generating a scalar value, it generates a scalar value that predicts the predicted outcome in positions stash, and all of its weights are set to the same value. So at random, we play game with the current policy network P and a previously selected policy network iteration. So this method of randomly selecting opponents from a pool stabilizes training by preventing overfitting to the current policy. So the weights are adjusted using stochastic gradient ascent in the direction that maximizes the expected outcome at each time step. So comparisons of evaluation accuracy between the value network and policy rollouts. So the current player wins in positions from the self-play dataset, and the AlphaGo's neural network architecture is depicted systematically. So these are all observed. So the Monte Carlo research in AlphaGo. So each simulation traverses the tree by selecting the edge with the highest action value Q plus a bonus based on the stored prior probability of the edge. So the leaf node can be for B, as the diagram depicts, the leaf node can be expanded. The policy network P possesses the new node only once and saves the output probabilities as prior probabilities P for each action. And C, the leaf node learning of convolutional networks is over 11% of games against each other and 12% against a slightly weaker software. So this weaker software the authors used is the Fugo. And when it comes to the D, the mean value of all evaluations in the subtree below that or below that operation is tracked by Q. So reinforcement learning of value networks. So the final stage of training pipeline focuses on position evaluation, which involves estimating a value function that predicts the outcome of games played from position S using policy P for both players. So the tree is explored using simulation, beginning with the root state. And each simulation's time step T chooses an action from state ST that is proportional to the prior probability, but decays over time to encourage exploration. So the tournament evaluation of the AlphaGo. So 3 points were observed. The outcome of the Go program tournament, and next thing is the AlphaGo performance for various component combinations on a single system. So in the version that only uses the policy network, there is no search. And see, a study of the scalability of the MCT tree, MCTS, the tree in AlphaGo with search threads and GPUs for 2 seconds per move using asynchronous or distributed search. So evaluating the player strength on AlphaGo. So using the value network, we evaluate all successors of the root position as a predicted winning percentage for the top evaluations are presented. So B, action values for each edge in the tree from root positions S, and averaged over value network evaluations, which is just equal to 0. So C, only rollout evaluations for averaged and the action values as well. And figure D, directly move the probabilities from the supervised learning policy network and are presented as a percentage, which is above 0.1%. And E, the proportion of simulations in which actions were chosen from the root. And F, the main variant from AlphaGo's search tree, which is the root with the most visits. And next comes the discussion part. So in this paper, the authors have created a Go program based on a combination of deep neural networks and the tree search that can compete with the best human players, compelling one of artificial intelligence's grand challenges. So for the first time, they have created effective move selection and position evaluation functions for Go that are based on deep neural networks trained using a novel combination of supervised and reinforcement learning. So they have developed a new search algorithm that successfully combines neural network evaluations and Monte Carlo rollouts. So this program AlphaGo combines these components in a high performance tree search engines at a large scale. So article 2 is mastering the game of Go without the human knowledge. So coming to the introduction part. So supervised learning systems have played an important role in the field of AI. So supervised learning has been fine-tuned to accurately replicate human expertise. However, the system has flaws that renders it useless. So this is due to the high cost of expert data. So if not completely available, if the data sets are available, ceiling systems based on supervised learning are imposed. The AlphaGo software has recently become the world champion in the game of Go. So the program's research analysis, locations, and selects moves using deep neural networks. So using the supervised learning, the policy network was taught to predict human expert moves and then modified using policy gradient reinforcement learning. So reinforcement learning in the AlphaGo 0. So this article mentions the use of the following. So the first is anything with the ability to detect its surroundings is called as an agent. So state the situation in which an agent is at any given time. Action, the action that an agent performs at any time. And the functions that determine the likelihood of carrying out a specific action is called in a given state is known as policy. So a reward is that what the agent received in exchange for performing a specific activity. And the long-term reward or punishment for the given state is known as value function. And the worth of state's activities that is represented by a value function, which is referred to as action. So Monte Carlo research. So there's always a possibility that the current best activity isn't the best action in tree search algorithm. So in these cases, the Monte Carlo tree search algorithm is advantageous because it continuously evaluates other options during the learning phase by executing them rather than currently perceived optimal approach. So this situation is referred to as the uh, exploration and exploitation trade-off. So it uses the action and tactics that have proven to become the most efficient up to this point, and also fully investigate the local space of various alternatives to see if they can replace the current best. Next is the reinforcement learning in AlphaGo. So these are the few other points. So the function of the MCTS in AlphaGo Zero. So the Monte Carlo research is heavily used as a game simulator by AlphaGo Zero. The actions of this research, on the other hand, are fictitious and do not exist in reality. So the Monte Carlo tree search algorithm is also involved in probabilistic search, which aids in determining the best neural network move. So as a result, the Monte Carlo tree search is used as a policy improvement tool, and policy for self-play based on the Monte Carlo research has been improved. So next comes the empirical analysis of the AlphaGo Zero training. So here they choose the next move within the Monte Carlo research modeling, again for the states in the simulation by using a formula U of S comma A plus Q of S comma A. So they repeat it. So the procedure is iterated until a node which has not been accessed, which is called as a leaf, until it's encountered. So with following an examination of the node V of S and V, and the backup is generated by the node S comma A, and the it counts the visitors and respond to the questions of the generated backup. So and continue with this topic. So along with the trees, search trees branches until you reach a leaf node as I've said earlier. So after that, the neural network is used to evaluate the node using the formula uh, uh, generated by V and B. So the tree that sprouts a branch where a leaf was previously present. So as a result, node at the top of the tree comes in picture. So when we have completed the 1600 tree search simulations, they choose the next action. So this is not imaginary, but rather an actual action thing. So next comes the knowledge learned by the AlphaGo Zero. So the learning curve of AlphaGo Zero over 40 days using a larger 40 block residual network. So the graph depicts so the player's performance in our reinforcement learning system iteration I. So the rating were calculated from assessment games involving various players using 0.4 seconds per search. So the final performance of AlphaGo Zero was trained for 40 days using a 40 block residual neural network. So the graph depicts the outcomes of a tournament between two players, AlphaGo Zero and the AlphaGo Master. So the final performance of the AlphaGo Zero. So in the evaluation performed by the authors, all programs were allowed 5 seconds of thinking time per move. AlphaGo Zero and the AlphaGo Master each played on a single machine with 4 TPUs. So the AlphaGo Fan and the AlphaGo Lee were distributed over 176 GPUs and 48 TPUs respectively. So they have also included a player based solely on the raw neural network of AlphaGo Zero, and this player uh, simply selected the move with maximum probability. And the conclusion for this. So as per the author's findings show that a pure reinforcement learning approach is fully feasible even in the most difficult domains. So it is possible to train to superhuman levels with no human example or guidance and with no knowledge of the domain beyond basic rules. So furthermore, when compared to training on human expert data, a pure reinforcement learning approach requires only a few more hours to train and achieve significantly better uh, significantly better performance. So using this method of the AlphaGo, they can easily defeat the strongest previous versions of the AlphaGo, which were trained from human data using the handcrafted features. And that's all about my presentation. Thank you.